Hello, I'm Durganshu from the Technical University of Munich, and today I'm going to give a short introduction about our research paper titled Towards a Unified Architectural Representation in HPCQC, Extending sys-sage for Quantum Technologies. One of the major areas of research in quantum computing is integrating QCs with classical HPCs as accelerators and not as standalone replacements to classical computers. This creates a very critical need for robust and modular software stacks, which can facilitate this kind of integration. Luckily, many researchers and companies are working on this challenge and creating state-of-the-art programming and integration frameworks. We also wanted to contribute to those efforts, and in this work, we expand the capabilities of sys-sage, a C++-based library. Traditionally, sys-sage is an HPC-centered library with a C++-based API to store, update, and provide all the relevant information about the system. This can mean static information like number of components, number of nodes, or dynamic information like bandwidth or latency values. Compared to vendor-specific APIs, sys-sage offers universality and ease of use by offering the possibility to unify multiple interfaces. When it comes to HPC systems, sys-sage relies on two central concepts, component trees and data paths. We found out that quantum systems can also be represented somewhat similarly because they also have a lot of static and dynamic characteristics. But they are inherently very different from HPCs, and they require newer representations and newer data structures for an accurate representation. So initially you have this tree-like representation in sys-sage for representing HPC systems. With our extension, uh, QPUs and HPCQC systems as a whole can be represented accurately in sys-sage. We found out that data paths are not entirely sufficient to represent QC systems. So we refined data paths and introduced relations which kind of generalize our data paths for the purposes of QCs. And you can find more details about the concepts in the paper. It's important to highlight that the role of sys-sage is not only limited to storing and representing this information in a nice way, but it's more than that. So we integrated sys-sage within MQSS, which is part of an initiative by Munich Quantum Valley. So we have a lot of raw data coming from QPUs, and we try to extract meaningful insights from the raw data. These insights can then be used by compilers, schedulers, or other tools. So we collected qubit properties on a 20 qubit quantum computer based on superconducting qubits and tried to calculate qubit qualities through some empirical formulations. The weights on the right are based on an empirical formulation for specific use cases which are discussed in the paper. These weights reflect patterns linked to QC topology. For instance, qubit 11 with 4 connections with may be unsuitable on some days, while qubit 13, which has like limited connectivity, might be better. These correlations are use cases and circuit dependent, but sys-sage's qubit quality data lets compilers map circuits to the best qubits for improved accuracy and fewer errors. Besides calculating qubit quality, sys-sage in its current shape can already address other problems like supporting schedulers and helping mappers to reduce shuttling operations. There are a lot of discussions in the papers which present all the details. That's it for now. Thank you for your time and hope to see you at ISC.